Hello, everybody, and welcome to today's Dynamics 365 Tech Talk. Today's topics will be an introduction to demand forecasting in Dynamics 365 supply chain management. My name is David, and I'll be your moderator today. We are broadcasting this session through Teams live events, and the audio can be heard through your device speakers. This session is being recorded on behalf of the Microsoft Corporation. When you join this event, your name, email address, and/or phone number may be viewable by other session participants in the attendee list. By joining, you're agreeing to this experience. The recording will be available on the Tech Talks Community Dynamics page within 5 business days. If you have questions for the presenters or need support, please use the Q&A panel located on the right side of your screen. Our presenters will be responding to your questions during the presentation, and there will be time at the end for further questions. Thank you for your patience during these announcements. Presenting for us today from Microsoft, we have Anne Krupke, Senior Fast Track Solution Architect. Anne, over to you.
Today, to help with Q&A, I have Nikhil Paldekar and Toby James, also from the Fast Track Group, and Andre Garmash, the Senior Software Engineer from the product team that works on demand forecasting. Thank you so much all for joining us today. A quick introduction, that's me. My name's Anne Krupke. I am a Senior Fast Track Solution Architect here at Microsoft, and you can see my contact information and my LinkedIn if you want to connect or give me a shout. This is part 1 in what is currently a 2-part Tech Talk series on demand forecasting in D365. This section will cover the Dynamics 365 aspect of creating a forecast, and our next session will focus on the new Azure Machine Learning Service setup and guidance. If there's a topic within the demand forecasting area that you're interested in seeing us cover in the future, please let us know in the chat or in the survey that David will post towards the end of this session. To keep things interesting, we've got a riddle of the day. The question is, how do sea animals forecast demand? We'll answer this riddle at the end of the presentation. If you've got any guesses, feel free to put them in the chat. Let's look at the agenda for today's session. We will begin by explaining what forecasting is and cover some background concepts. Then we'll take a deep dive into the various forecasting algorithm parameters in Dynamics and what that means for us as we implement this functionality. We will then cover the other setups required on the Dynamics side to use forecasting, and then we'll go into a demo of generating a forecast and reviewing the results. At the end, we will cover best practices for implementation and additional helpful resources, and then we'll wrap up with Q&A. Most, if not all of you here today are probably familiar with what forecasting is, but I want to take some time to review the basic concepts involved in forecasting so we can better understand how it works in the system. First of all, what is demand forecasting? Demand forecasting is the process of predicting future demand for products and services to estimate our revenue and drive strategic and operational business planning, among other activities. Why is demand forecasting useful for businesses? As we said before, forecasts allow us to predict that future demand, and we use that to drive certain business decisions. When we have greater certainty in our expected demand, we can minimize our buffer inventory as a result, which reduces the amount of money we can tie up in our on-hand inventory. It also helps us avoid the cost of expediting procurement or production due to unexpected demand. Another benefit of demand forecasting is that it can allow us to reduce our lead times. In a make-to-order model, our fulfillment lead time will be constrained by our procurement and/or production lead times. If we use a demand forecast to drive our processes, we can order or make longer lead time items ahead of time, reducing the amount of time from sales order entry to customer delivery. Forecasting also allows us to look at our holistic demand over larger periods of time. This can be useful to drive global capacity planning and feed into our strategic planning processes. And thirdly, in industries such as retail, having inventory on hand at the time of an order is critical. If we don't have it, the customer will go buy it somewhere else rather than waiting for us to buy or make more. An accurate demand forecast can help us prevent stockout scenarios like this and allow us to gain the revenue that we would have otherwise lost in a stockout. Here we can see an architecture diagram of how forecasting works when we use Dynamics 365 supply chain management. We use Dynamics, Azure Machine Learning, and Azure Data Lake to support this overall process. Today, we will be focusing on the processes that take place in Dynamics 365. Our next Tech Talk in this series will focus on the other components in more detail. However, I do want to note that Azure Machine Learning uses the tool R, and specifically a package called Forecast, to generate the forecast equation. If the R package is a free and open source tool that's available to everyone. The main strategy used to generate forecasts in Dynamics 365 supply chain management when we use Azure Machine Learning is time series forecasting. Time series forecasting refers to models that use previous demand values to predict future demand. We can break the general components of a time series forecast model into 3 buckets. First, we have the trend. Trend is the general direction in which our demand is moving, i.e. increasing or decreasing. Next, we have seasonality. Seasonality represents repeating short-term patterns in our demand. For example, we may have a trend in demand where we see a spike at the end of the quarter due to a push to close sales, or we see an annual pattern where demand spikes during our summer months. Seasonality does not have to relate to specific seasons of the year, although it certainly can. Next, we have error. Error or noise refers to the unexplained or random variation in our time series. In real life, there's no way to create a model that explains our trend and seasonality with 100% accuracy, so there will always be some degree of error. When we add the 3 different components together, we can predict our demand. The different statistical forecasting algorithms used by Dynamics and other forecasting tools will calculate and combine these general components in different ways, allowing us to compare different forecasting models and select the one that best seems to predict our demand. At the core here, what we're trying to do is take these components and figure out how to build an equation that outputs expected demand for different points in the future. When we generate a forecast with time series models, we use our demand history data points to build out the forecast equation and estimate its accuracy. Let's review on a high level what's happening when we do this using Dynamics and the Azure platform. We start by taking a subset of our demand history data, and we use the parameters we've set in Dynamics and feed the information into Azure Machine Learning. In Azure, the statistical modeling tools essentially create an equation to predict future demand. This equation is comprised of different terms that reference the demand history points, which are significant in estimating the future demand amount. In most cases, these historical values are multiplied by some factor determined by the statistical modeling tools and our parameters. There can be many terms as part of the equation, and it can be much more complex than taking previous history and multiplying by a factor. But for the sake of understanding the background, I've kept this example very simple. And as mentioned, there's normally an error term in this equation. The output of the equation built in Azure is our expected demand value at time t. When we generate a forecast for the next year, for example, we will use this equation to get the values of demand for t is January, t equals February, etc., etc. Dynamics 365 does not return to us the quote-unquote equation that is derived by our forecasting tools, but I want to make sure we understand what happens after we click that Generate Forecast button in Dynamics. Now, as we remember, we only use a subset of the demand history to generate the forecast equation. The remaining data points we keep in reserve will then be used to estimate the accuracy of the equation that we built. When we're trying to determine which model best fits our demand, we use the indicator called mean absolute percentage error, or MAPE, to analyze how accurate our forecast is likely to be. To calculate MAPE, we take the data points that we did not use to build our forecast equation, and we calculate the forecast for those dates according to the equation that we developed. So as we can see here, we have the purple data series, which is the actual demand values that we kept in reserve. And now we've added the light blue data series, which is what our equation would have forecasted for those dates. What MAPE is doing on a high level is comparing the actual versus the forecasted value for our data points between these two different data series. This will give us a measure of how close the forecasted values are to actual demand, which then indicates how accurate our forecast model is. We can see here the specific equation for calculating MAPE, where A is the actual value of our demand and F is the forecasted value. The difference between those two is divided by the actual value A, which gives us the percent difference between the two values. We take the absolute value in this ratio because we don't care about positive or negative, just the distance between the two. And then we sum and divide by the total number of points, which gives us the average percent difference between our data series. MAPE is expressed as a percentage, as indicated on the equation on the screen here. The lower the value is, the more accurate our forecast likely is. In general, a MAPE of 20% or less would be pretty good, but 10% of course would be even better. The best MAPE value that you can achieve is going to be very dependent on the amount of your data and how volatile the values are. When we generate our forecast, we need to determine what dimensions we will include. The mandatory dimensions are company, site, and allocation key. If we want to be more detailed in our forecast, we have several more dimensions to choose from: country/region, state, customer group, customer account, warehouse, inventory status, and item number and dimensions, which references the product dimensions, size, color, style, and configuration. When we're implementing demand forecasting, we'll see the term granularity attribute frequently, so let's discuss what that means. Let's say my company has chosen the purple highlighted dimensions to include in my forecast: company, site, allocation key, country, customer group, and item number and dimensions. When I generate my forecast, I'll get values for each of the rows in the table here, and possibly many more rows. Each row in the table represents a unique combination of the forecast dimension values that I've enabled, which is otherwise known as a granularity attribute. When I build a forecast equation, as discussed in the previous slides, the forecast will be run for each granularity attribute that I have based on the forecast dimensions that I chose. It's important to understand this because it affects your results. For example, if I run my forecast at the customer account level and sum it, it may not be the same forecast amount as if I ran on the customer group level instead. In other words, aggregating detailed forecast lines is not necessarily going to give us the same result as running the forecast with fewer dimensions. Now that we understand overall what's happening when we ask Dynamics to generate a demand forecast, let's dive into the parameters available to us in the system, which can help impact how the forecast equation is calculated. This screenshot shows the list of different parameters that we can set in Dynamics that will then be used by Azure and R to create the forecast model. In this section, we will dive into each of these parameters and how they impact our forecasts. The first parameter we will talk about is the time series model. This equation determines which statistical model is used to calculate the forecast equation. For this and the other slides in this section, you can see that I've added at the bottom the information for the specific parameter as it relates to that slide I just showed. Our first option for time series model is ARIMA, which stands for Autoregressive Integrated Moving Average. Next, we have ETS, which stands for Error Trend Seasonal. It is also known as exponential smoothing. With this method, we consider our more recent demand history with heavier consideration when we build our formula. The third option is STL, or Seasonal and Trend Decomposition using LOS. Decomposition means that we're going to separate out seasonality, trend, and error in our data and add them all back together at the end. STL does particularly well when there's a lot of data missing in your demand history. These next two options are combinations of models we've already shown. We have ETS plus ARIMA and then ETS plus STL. And finally, we have the option All, which directs the system to run through all of our options above and pick the model that gets created with the lowest MAPE value. If you don't have a data scientist to direct you, or you're just trying to get started quickly, you would probably start with all and then analyze your forecast outputs to see what model was chosen and how it looks. One thing to note is that all may take more time during forecast generation, since it's going to run through every option and then pick one. ARIMA is another model which can take some time to generate the forecast, so it's good to be aware of how your choices for this parameter can impact the forecast generation process. Next, let's talk about our minimum and maximum forecasted value parameters. Essentially, they allow me to choose what the limits are on the values that my forecast can have. For example, I may set my minimum value at 0. If the system doesn't think I'm going to have demand for that date, I don't want to put anything there. Now let's say I want a maximum value of 24 for some reason. We notice that the forecast in this case would have given us a value of 25, which is above our maximum allowed value. So instead, the forecast will come out with the value of 24 for this data point. The next parameters relate to what happens when we have gaps in historical data. When we don't have data for a certain time in our history, we need to decide what to do with the gap. This is answered by the missing value substitution parameter. We can specify a number, we can use the average of the previous and following data points, we can just take the previous value, or we could do a linear or polynomial interpolation to guess at what that number would have been. However, in most cases, you probably just want to use 0, because if we were missing data, it's likely because there was no data or no demand on that date. The other thing we need to decide is the scope of the missing value substitution choice that we just made. We can apply it for our whole history, for the date range of our forecast run, or just for a specific granularity attribute, which we mentioned as a concept earlier. In the vast majority of cases, we recommend using the global setting here, which applies the substitution to all of our data. Next, we have the confidence level parameter. A confidence interval represents the range of possible values that we think demand might fall in. In this screenshot, the confidence interval is represented by the shaded blue region. The purple line represents our forecast. If my confidence level is 95, then the shaded region will show the range, which contains the actual future demand value with 95% probability or confidence. The bigger the number of our confidence level, the larger the shaded region will be. The parameter ranges from 1 to 99% in most use cases, and it's primarily going to impact how you view the outputs of forecast generation, but not actually the forecast demand amount. As we discussed during the concept section, one of the components of the forecast can be seasonality. Looking at the sample data below, we can see that it looks like there may be a seasonal pattern. The seasonality hint parameter allows us to tell the system on what interval we think our seasonality pattern repeats. For example, if we have a quarterly seasonality pattern, then we're forecasting in monthly buckets, we would put the value 3 in our seasonality hint field. When we do have models that use seasonality, we have the option to specify what the relationship between trend and seasonality is. One option is to define the relationship as additive. What this implies is that our seasonality impact is independent of our trend. We see this represented in the chart shown above, where the seasonality pattern remains the same, pattern and magnitude remains the same despite the fact that we are overall trending upwards. Our other main option to define the relationship is multiplicative. This implies that seasonality and the magnitude of seasonality is dependent on our trend. As our trend goes up here, so does the magnitude of the seasonality as shown in the graph. We also have the option to specify none or auto as our value in this parameter. If we don't know which to use, then we should choose auto and let the system identify the right option. And finally, our last forecast algorithm parameter is the test set size percentage. This allows us to define the amount of data set aside for testing the accuracy of the forecast versus how much should be used to generate the forecast equation. For example, if we set the test size percentage at 20%, we would use 20% of our historical data as the test points to calculate our mean absolute percentage error. And the remaining 80% will be used to build the forecast equation as we discussed earlier. Overall, 20% is a good value to start with for our test set size percentage. You want to make sure that you use enough data to get a good MAPE measurement, but you also want to make sure that the forecast model has enough data to generate a good forecast. Additionally, bigger values in this parameter could have a forecast performance impact. Now that we've covered the different forecast algorithm parameters available, let's quickly run through some guidance that we have to share. First and foremost, test, test, and retest. You'll want to tweak the different parameters and compare the forecast results and the MAPE on the different types of outputs to arrive at the best configurations for your specific data. One good way to analyze forecast outputs can be to compare your previous year's demand history and look at how similar or different the forecast is comparatively. Secondly, I cannot recommend enough that you include a data scientist in your implementation of forecasting functionality, because it helps you really dive into the detailed areas of configuration and it keeps you from getting stuck with a flat forecast. And lastly, I want to point out that there are parameters which are available to us in Dynamics do not represent the full set of parameters used by the R forecast package. The additional parameters either have no values or use some defaults that you can't change from the Dynamics user interface. If the results you're getting with basic configurations are not working well enough, then the next step should be to review the other parameters available in the R package and figure out whether those need to be adjusted. In the next Tech Talk in this series, we'll walk through a scenario of when you might want to do this and cover the high-level procedure to achieve this. Now that we've covered the different statistical parameters that we can configure, let's look at the remaining configurations to do in Dynamics in order to use demand forecasting in the system. First, we have our demand forecasting parameters. On the General tab, we defined our demand forecasting unit. It's important to know that you must have unit conversions set up for all items that relates to the demand forecasting unit if you want to be able to generate a forecast. You also define in this page which types of transactions should be included in our historical data set and what our strategy for forecast generation is. The options are for forecast strategy to manually forecast, to copy historical data from previous dates, or to use the Azure machine learning service, which is what we focus on today. Before 10.0.24, the forecast strategy for Azure was the Azure Machine Learning Classic, which is a service that's going to be deprecated. As I mentioned before, the next Tech Talk in this series will talk about the new Azure Machine Learning service, how to set it up, and implementation guidance to use this tool. In the Forecast Dimensions tab of our parameters here, we're going to specify the granularity we will use when we generate forecast lines. As I mentioned before, company, site, and item allocation key are mandatory to include in our forecasts, but we can choose for the additional options which ones we want to include. Next, we have item allocation keys. These are groups of items that we want to generate a forecast for together. One benefit of item allocation keys is that it allows us to improve the performance of forecast generation in a process similar to batch threading, where we can work on different allocation keys in parallel to generate our forecast. We can also choose to define different values for our forecast algorithm parameters for each item allocation key that we have. For example, I may want to have one item allocation key which contains items that I want to run using the ARIMA time series model, and another key with items that I only want to run using the STL time series model. An item must be part of an item allocation key in order to be included in the forecast generation process. The next configuration is forecast models. Forecast models let us track multiple different forecasts in the system while still keeping them separate. You may have different forecast models for the system-generated forecast, the forecast provided to you by your customers, or the forecast generated by the sales team as examples. We also have the option to create outlier removal queries to prevent anomalies in our demand history from affecting our forecast generation. For example, if I'm a wholesaler and an online seller buys 1 million units of my stock in a once-in-a-lifetime order, I may want to remove that demand from my history when I do forecast generation. So to achieve that, I would build a query to remove the sales order number specifically from my historical data considered by the forecast generation process. If we have multiple legal entities and they have intercompany operations, then we want to set up our intercompany planning groups. This allows us to define the sequence in which our demand forecast should be generated by company. We want to set up our downstream companies to run first, and then have our upstream supplier companies that ship to the downstream companies second or afterwards. And finally, if we're going to generate a master plan and planned orders based on our forecast, there's additional setup to complete. On our master plans, we want to define the forecast model that should be considered when we're looking for demand requirements from our forecast. We also need to define our forecast reduction method, or what do we do when we start having real sales orders come in or other demand for a forecasted period. We can choose to reduce our forecast by the quantity of actual demand transactions that we've received, either periodically or in real time, or we can reduce the forecast periodically by some percentage defined by us. Now that we've covered all the setups that are necessary, with the exception of the Azure Machine Learning service, which will be covered in the next session, let's take a look at the process for generating a forecast from the dynamic side. We'll first start by walking through the different steps of our high-level process. First, we gather our historical data. If we do not have enough history yet in Dynamics, we can use the data migration framework to import external historical demand. Next, we trigger forecast generation on the Azure side, which will create the forecast model as we explained, and then test the mean absolute % error for the model. Once we're done in Azure, we can review the generated forecast in Dynamics and update the values manually as we see fit. When the forecast is satisfactory, we then authorize the forecast, which publishes it to the system for use in planning and other activities. Now let's transition over to the system to demonstrate what the process looks like. To generate a demand forecast, I'm going to navigate to the master planning module, and in the forecasting area, I'm going to click Generate Statistical Baseline Forecast. On the form that comes up, I'm going to have a number of values that I want to set. The first thing I'll do is define my historical horizon, which is the dates of our history of demand that I want to be used to generate the forecast. So I can set the dates here. In general, the historical horizon should be twice as long as the forecast horizon. So if I'm forecasting for the next year, then my historical horizon should contain at least 2 years of data. And if we have seasonality patterns, we want to make sure our seasonality cycle is repeated at least twice. I'll then specify the date I want my forecast to start. And in this case, I'm just going to build a forecast for my dealloc item allocation key. I can choose what the buckets I want my forecast to come out in, day, week, or month. And in this case, I want month. I'll set my forecast horizon, which tells us how many buckets into the future we're going. So 12 months is a year's forecast. I can also set a freeze time fence if I don't want the next couple months or something for, like, in that case, to be edited, but I'll just leave that at 0. I do have the option to run forecast generation in the background as a batch process, but in this case, I'm just going to run it from the front end. So I'll click OK, and I'll get a notification from the notification menu when this process is completed. To view the results of a forecast, I'm going to navigate back into the master planning module and click Adjusted Demand Forecast. This shows me the lines of our forecast that were generated by the run that I just did. We'll notice that most of my lines all have a value of 1 in the forecast. That's because I didn't have any demand history and my forecast minimum value is 1. We're going to focus instead on this top line for item D1, and we can see in each of the columns we have the forecast amount produced by the system that it thinks we will have for demand for the next year. If I want to change any of these values, I can do so by typing in the box that we see here. So I can change this to 1202, for example, and it will save that value. If I want to see more details, I can go to forecast line details here to dive into where this forecast came from. The first thing that I see here is my historical demand that was used. So when I defined my historical horizon, these are the data values that were picked up by the system, and we can see all of the different values for the different months. I didn't have a historical forecast because this is the first forecast I've been generating. In this next tab, I can see the forecast that was created by the system. That one entry that I manually edited is bolded to reflect the fact that I did manually adjust it. And in the second row here, I can see the amount by which I did the adjustment. So we have that traceability to any manual adjustments made to our forecast and what that was. So for each of the months for the next year, the system has produced a value, and we've got the confidence interval based on the parameter I set for the confidence level. Since I chose all as my option here, in model details, I can see that we looked through all the models and chose ARIMA as our forecast model, with our MAPE for this model being 0.67, which is incredibly low, which is easy to do when you're playing around with demo data, but not as easy to do when you're using real life data. And our bottom tab here, we can graphically see all of the information that we're working with. The dark blue line on the left represents our demand history that was used by the forecast model. The orange line here is our historical forecast, which, as I said, is 0 because I've never generated a forecast for this item before. But if we did have a forecast, we could compare to the history. The purple line over here on the right is the forecast that's been proposed by the system. So we can see what that value was and compare that pattern to our previous demand. We also have the blue shaded region, which represents the confidence interval. The width of the confidence interval, again, is controlled by the confidence level parameter that I set in the system. We've got a key for this information at the bottom as well to reference when you look at this report. So that's the outputs of a specific granularity attribute that was generated by the forecast. Once I'm happy with my forecast and adjustments, I can authorize that forecast, which publishes it to the system. So here I specify the dates that I want to publish for, whether I want to save my manual adjustments, which company and which forecast model I want this forecast to be published to. When I'm happy with everything, I'll click OK, and that will publish my forecast to the system, which will allow it again for use in planning and other activities. Now let's move on to our last section, which is our resources and recommendations. We have a few do's and don'ts for high-level guidance for when you're implementing this functionality. I absolutely recommend that you include a data scientist in your implementation or someone with a statistical background who understands the different pieces of the functionality that R is doing, what the parameters are in Dynamics, and what the parameters are that we don't see from Dynamics. As I mentioned before, when we're generating a forecast, you want your historical data to be at least 2 times as long as your forecast horizon length. So again, if I'm generating a forecast for a year, I want to use at least 2 years of historical data to back that up. And if I have seasonality, which is that short-term pattern that reoccurs, I want at least 2 cycles of seasonality to be included in my demand history. When you're implementing this functionality, we recommend that you test different values in the forecasting algorithm parameters and look at the impact that has on your forecast results. Just this module is not one size fits all with the configurations. You're going to have to customize it based on your company's data and the kind of trends and patterns that you have. If you're trying to implement this functionality as part of a go live in general for Dynamics, then you're not going to have demand history in the system, at least not at the beginning. We do, as I mentioned before, have a data entity called historical external demand, which allows you to load the demand from your legacy system into Dynamics for the purpose of forecast generation. With one caveat, it wipes that entity out every time you generate the forecast. So you'll need to load the demand, external demand, every single time you generate a forecast, which is why we recommend that you define a process for how you will do that in the interim until you have enough data in Dynamics to be able to generate the forecast without needing to do that. This legacy demand data may not be formatted the same as Dynamics data, which is an important consideration. So you may not have the same item numbers, the same warehouses, customer groups, etc. And if you want to use your legacy data, you may need to go through some extensive transformation so that it can be digested by Dynamics appropriately. For this reason, a lot of customers consider implementing demand forecasting as a phase 2 or further of their Dynamics implementation in general, so that they don't have to go through that process of figuring out how to massage the legacy data so that it's compatible with Dynamics. So that's one of our options, is to just implement Dynamics and then come back after a certain amount of time and implement forecasting just using the data we have in the system. Over on the don't side, the first one is I highly recommend that you look at your demand history data before we start configuring the system, understanding the shape of the data and the trends and missing data and why is it missing, really and which products behave similarly and which ones don't. Really getting to know your data before we configure this system will help us understand how we need to configure it to get an accurate forecast. One of the questions we hear all the time is, why do I have a flat forecast? And I know that it can be very discouraging, but don't give up. There are, again, those different forecast algorithm parameters that we have available in Dynamics, as well as the parameters available in R. So if what's happening in Dynamics is not enough for you, please come to our next Tech Talk, where we'll talk through an example of how we needed to go into the R side of things and add an additional parameter to be able to control our forecast more accurately. If you have intercompany operations, you're buying and selling internally, make sure you set your intercompany planning sequence. Again, we want our downstream companies to get their forecast done first, and then our upstream companies we want to do afterwards so that we can reflect that impact of the downstream company's forecast. As a reminder, we want to be careful of our test sample size. The higher that value is, the less data we have to build our forecast model, and the more of a performance impact we may see on the forecast generation side. If you're using your forecast to drive master planning, make sure that you define your forecast reduction method. You want to avoid double counting actual demand with your forecast, unless for some reason your business process wants to look at those separately. Here I have a list of additional resources. When the PowerPoint is posted along with the recording for this call, you'll be able to access them. We have the Microsoft Docs site, which contains several pages on how to set up demand forecasting, what the different configurations are, with a section for the Azure Machine Learning Service. There is a recently created group in the Yammer Finance Operations Insider Program specifically devoted to demand forecasting. So if you're not a member of that, it's a good idea to go check that out and use that to foster communications with the community or ask the product team questions about forecasting. As I've mentioned a few times, the Azure machine learning side of things is using an R project called Forecast, or R package called Forecast. If you want to understand more about that, then I would recommend that you access this comprehensive R archive network website. It has user manuals. It lets you look at what's happening there, what the extra parameters are, and hopefully will round out your understanding of what's going on when we generate a forecast. And of course, if you have any feedback about things that we can add to the product, you can create an idea on our ideas portal, which I have linked here at the bottom. And also, please, vote for any other ideas that you think are important so that we can take that feedback to the product team. That brings us back to our riddle of the day. The question was, how do you see animals forecast demand?
I don't know, Anne. How do you see animals forecast demand?
They use algorithms. Hopefully that was an interesting brain teaser. I enjoy these jokes. They make it fun for me. With that, we are going to take it over to the Q&A portion of this Tech Talk.
So we did have some remaining questions. There was one about grouping. So when we're doing a forecast, maybe sometimes down at that lower item level is too granular, and we want to be able to group items and forecast, sort of have a forecast that applies to a group of items. Mm-hmm. Is that possible? Is that something we're looking at for future capability?
So you do have the option to not include item number in your forecast, as we covered earlier. Let me go back to the parameters. If we look here, you can see we always use company, site, and item allocation key. So we do have the option to remove item number from our forecast dimensions and just forecast at the item allocation key level, which is a group of items.
Right. The other common question that was asked a few times, so it's probably calling out, was around different variations of, say, if we've got a particular SKU and then we retire that SKU or supersede that SKU with a new SKU, but we want to actually rely on the history of the old one. So we posted a suggestion there that you could export that historical sales or history for the old one and sort of change the data to align with the new, and then import. But obviously there's that implication of maintenance of that data, as Anne pointed out, for running for every forecast. So I think there were some other scenarios about maybe you've established a new store and you want to base the forecast on a previous store or warehouse. So you could look at similar techniques. So there's nothing native there that would automatically do that for you.
That's correct. We don't have a item supersession functionality directly in the system, so you would have to follow the method that you outlined there. If that's something that there's interest in adding, as always, feedback can be posted to the ideas site, and ideas with a lot of votes are often considered by the product group for inclusion in future waves of our roadmap.
Here is another interesting one, to put someone on the spot. How realistic is it to assess sort of the seasonality on a weekly basis with the forecasting feature?
I think it's going to be the fun answer, which is it depends. It depends on how much data you have and how many gaps in the data that you have. So, that's a very granular level, right? To get weekly data, and if you're going to a deep granularity with your forecast dimensions, you may not have sufficient data to do that. So that's one of the reasons that you're going to want to first understand your data and then play around with the different, forecast dimensions and algorithm parameters in the system to see what kind of MAPE value you get out of trying to predict that kind of seasonality. I don't know, Andre, if you have anything you want to add to that one. Okay.
Oh, I think your answer basically is quite complete.
Okay.
Yeah, we suggested that yeah, it should be possible to export the history and edit it and import again. That's basically rather workaround.
Okay. There is actually here's a good one. The dimension country region where's that from? Is that from the customer? Is that the delivery address of the order? What's the source of that dimension?
That's a good question. I'm not sure off the top of my head. Andre, do you know the answer?
I would need to have a look at the code. It would be possible to follow up on that question?
Yeah, that's totally fine. I think so. We will investigate and get back to you on where the country region comes from.
Okay, that's pretty much all the questions answered. Yeah, there haven't been any new ones coming through, so back to you, Anne.
Okay. I'm just taking a quick look through our new questions. There was a question, do we have the option to consider historical sales data and not actual sales orders? So using the data uploaded in the staging table, but not actual sales orders for statistical generation. Andre, I would ask you if you know the answer to that one, or if we need to follow up on that.
Could you please repeat the question? You mean?
So we have that option in our parameters to include or exclude certain types of transactions here, right? Yeah. If we turn sales orders off here, but use the external history entity through DMF to load demand, would that work as a strategy for generating a forecast?
Yeah, absolutely. Because there was a question about making it more transparent in terms of what is going on in terms of data preparation, and I think we really need to improve the documentation. But these are basically two different steps. We take in inventory transactions into the source for forecast generation, and we're also considering all the external historical demand, which we are not segregating, whether it's sales or something. So yes, short answer is yes, it will work.
Okay. We have a question. Why do you have to upload historical data every month? I was assuming that you upload the system continues with the actuals. So in a kind of related note, if we have transactions in the system and we have these transaction type flags set to yes, we don't have to do anything there. But if we are using data from a legacy system, say I've only been on Dynamics for 3 months and 3 months is not enough data for me to generate my forecast, then the additional year and 9 months I need to load in for the process to use to have enough data. Then when I run, so I use data migration framework to load the external demand history entity, and then that gives me 2 years of data. but when I generate my forecast, it wipes that entity out. So if I want to then in another month generate my forecast, I've got 4 months of data in the system now, but I need a year and 8 months. I have to load that again to get 2 years of data when I generate my forecast. But when I've been in the system for 2 years, I no longer have to use that data migration framework process because I have enough data to generate a statistically significant forecast. Another good question was, is production consumption items considered for forecasting? And the answer is yes, and that's why we have these transaction types here, right? So demand, when we talk about demand, a lot of times we imply that it's just sales demand, but there are many types of demand that can occur in the system. For example, production line, right, which is when we consume raw materials into a production order. So that's something we have the option to say, yes, I want that as demand. I want to generate a forecast for raw materials or sub-assemblies, because as we mentioned at the very beginning, you know, I may want to procure my raw materials that are very long lead time based on a forecast instead of waiting for an actual demand signal to do that. So yes, we can forecast for things that are consumed in production, as well as many other types of transactions that we see here. I saw another question about being able to load a sales forecast and then manually editing it. And the way that works, we have, like I mentioned, our forecast generation strategy for Azure machine learning, but we also have the ability to manually enter forecast lines, which I didn't show today, but it does exist. So if we go to add a manual forecast line or upload via Excel, we can put whatever we want in those values, and we could have it be a customer forecast model so we differentiate it from system generated. So we can load manual forecast lines into the system and adjust them as we need based on, you know, the information that we know. So it is possible to, one, manually enter our own forecasts and then to edit them after the fact.
There's a good question, and I'm not sure if we can answer it straight up here, but I'll put it out there around how we could go about estimating the license costs for the sort of machine learning component, right? So any guidance around the, you know, whether it's based on volumes of data, performance, SLAs, or anything like that, or is it a matter of running some tests to determine what's required? I'm not sure, Andre or Anne, Mikhail.
Yeah, that should be pretty straightforward. As far as I remember, Azure has this price estimator, plus it gives a pretty good breakdown in terms of what are the costs, I think down to resource group. So if you are running the demand forecasting in separate resource group, it should give you an overview how much money you're going to pay for it. But basically, most expensive part in running demand forecasting in Azure is actually compute resource, compute cluster, which is going to run this R scripts. And here users have, of course, a lot of flexibility as to what they want to achieve, whether make it fast but slightly more expensive, or slow but cheap. And of course, it's possible to configure it so that users will pay only for the usage.
And it also, there's going to be a number of factors, right? Sort of the volume of data, the different forecasting parameters, or the algorithms that are used as to how much compute and so forth.
I don't think that parameters will significantly impacted, because it would change the output, of course, but the time it is needed to generate the forecast might vary just so little that it almost have no effect on the end cost.
Okay.
I think this has been followed up by another good question, which is the Azure cost will that be in the customer subscription or the Microsoft subscription?
It's a customer subscription.
Mm-hmm. And from a D365 licensing perspective, no additional licensing is required to generate the forecast. The additional cost would come from the Azure side, just to round that out. We have a couple of questions about the performance side of things, and I think Toby, you and Nikhil are planning on addressing that in more detail in the next session. Is that correct?
Yeah, correct. We'll talk more about the performance in the next session in a couple of weeks.
Okay. We have a question: can the forecast be updated every quarter based on the previous quarter, or based on management decisions to change the current forecast? That's a good question. The answer is yes, we can regenerate a forecast at any point in time, and we can override what's currently published if we want to, especially if we want to incorporate data that's just occurred. And as I showed during the demo, we can manually adjust the forecast before we publish it, and we can manually update forecasts afterwards as well. So we have that ability to rerun the statistical forecasting piece, and we have our ability to manually adjust the outputs as well. Okay, any other questions that we see that we want to talk about? Oh, here's a good question. Is there a way to forecast demand with other methods than just historical? For example, supplier forecasted supply or global supply chain disruptions? So the short answer from my perspective is not in Dynamics. Yes, it's possible in general to forecast off of things other than just demand history, but the process that Azure Machine Learning uses for Dynamics is time series models, which specifically are based on historical demand data and nothing else. But it's not uncommon for people to want to use other factors to help estimate future demand. It's just not something that's included in the way forecasting is run in Dynamics. Andre, do you want to add anything to that?
Yeah, certainly. You're absolutely correct that it's a univariate. We only take, it's basically time series prediction, and we only take historical demand to produce future figures, and in this way it's a bit naive, but the way it's built, it's quite extensible, so it is possible to incorporate external numbers, and but then partners would have to customize the R script so that it takes multiple numbers, and so that the forecast is actually multivariate.
Thanks. Okay. And another question for you, Andre. Is it possible to add more forecast dimensions in code? I think this is a pretty common request.
It should be possible. It's all based on enumeration, which is, I bet it's extensible. So the way to start would be to add enumeration item there, and then it would be possible to configure an extra dimension in the UI, but of course it would require multiple places to extend the code in multiple places so that we take the source data for the dimension.
Great. That is all the time we have for questions. If we didn't get to your question, we will follow up afterwards. Thank you so much for attending. I'm going to turn it back over to David to wrap us up.
Thank you very much, Anne. I've posted a link to a short survey in the Q&A panel, and we'd like your feedback on today's session and hear what you'd like to see in future events. Thank you for your participation. As a reminder, the recording of today's session will be available on the Tech Talks Community Dynamics page within 5 business days. I'd like to extend a big thank you to our presenters and audience for joining us today.